To calculate the arc length of the curve in parametric, let's paint and curve in parametrics. So let's say, for instance, if we have, let's say, a curve like this, and we want to calculate the length, for instance, from here to here. So we are going to divide, as always, the curve in little pieces, where each piece is going to act as a line. And so then we're going to integrate and calculate the whole length as we have done before. For instance, to calculate the length of this straight line, assuming that this is a really small piece of the curve, we are going to consider that this piece is a straight line. And so we have here a triangle. Let's say this is the base and this is the height of the triangle. And so in this little triangle here, what we want to calculate is the length of the hypotenuse, right? But we know that the length of the hypotenuse by Pythagoras is equal to the square root of this side square that we are going to call it dx, this little variation there of the x, I'm going to call it dx, so this side square plus the other side square. This is the little variation of the y, so I'm going to write this as dy square. So this is the length then of this hypotenuse here, of this little piece of the curve. Some algebraic transformations here is this expression we multiply and divide by the same sign, does not vary. And so algebraically this is going to be equal to the square root. I'm putting this dt inside of the root as a square. And then this is going to be the same that dx over dt, the whole sign square, plus dy over dt, the whole sign square. And so this dt. So we have then that the length of this little piece of the curve here is equal to that. So now to calculate the whole length of the curve from the first value of t that we want to the last one, we just have to integrate the whole thing. So the length of the curve from, say, certain parameter a to wherever we want to finish, so we have to just add all these little pieces from t equal the first value of t and the last value of t here. So the length of the whole curve is going to be equal to the integral from, let's say, t0 to t1, the first and the last value of t, of this expression that we found here. That is the derivative of x squared plus the derivative of y squared, the square root dt. So this is going to be then the formula for the arc length of a curve in parametrics. And remember that what goes here is just the derivative of x, and what goes here is just the derivative of y. This is then for any function in parametrics x, y, depending on t. And we will see in a moment how do we calculate this in a concrete example. So the first example, let's consider the curve given by the x and y like this. And I want the arc length when t belongs to the interval 0 to pi. I mean the arc length of this curve from t equals 0 to t equals 2 pi. If we draw this curve in parametrics, we will see that this is just a circle of radius 3. You can draw this curve by doing a chart and assigning values to t, or you can do it in Sage. In any case, this is a representation of this graph. So now we just apply the formula for the arc length that we have seen before. So that is the arc length of this curve is going to be equal to the integral from the first value of t which is 0, to the last value of t, which is 2 pi, of what? Well, we are going to put here, following the formula, the square root of, and so here will go the derivative of x squared plus the derivative of y squared. Well, the derivative of x is x is 3 sine of t, the derivative is going to be 3 cosine t, and that have to be squared plus the derivative of this, that is 3 minus sine, the whole thing squared, and so dt. We do the operations here, and this will be the integral between 0 and 2 pi of square root of 9 cosine square of t plus 9 sine square of t dt. Now let's just do the algebra here. So this is the integral between 0 and 2 pi of common factor here 9 between these two terms, and remains in the first term cosine square plus sine square, which is of course 1, and so this is the integral between 0 and pi of the root of 9, I mean just separating here the roots, which is 3, and the root of 1, which is 1, so it's just 3 dt. So the 3 goes out of the integral of 1 is t, evaluated between 0 and 2 pi, and so we get just 3 multiplied by 2 pi, which is 6 pi. A number that is not surprising, since we were calculating the length of this curve from 0 to 2 pi. Essentially, we are calculating the circumference of this circle, which is a circle of radius 3. So we know that we could have predicted that the length was going to be then 6 pi.